Okay. Okay. Uh, for today's course, for this morning session, I will continue and finish up the Laplace or all the Laplace that we will have. Okay. I will review a little bit and then we can move to new sections. The last part in the Laplace, which is the Dirac Delta. But if we still have time, we can have uh, some some practice in Laplace. Okay, and for preparation for midterm, uh, we can have some review on afternoon class. Okay, afternoon class. So afternoon class, I will divide by maybe the first hour is going to the new chapter, uh, just to see what we are going to learn, and then after that, in the afternoon class, we will have the um, practice or exercise, okay, especially for the higher order differential equations, okay, to recall what we have learned and what we might have in our midterm, okay, next Friday. Okay. Okay, so don't forget, next Friday, uh, July 22nd, we will have midterm, right? Okay. Now go to let me give you some idea on first is the Heaviside function or the unit step functions. Right? Let me give you idea. Okay, first is this. Okay, imagine the first one is our original function. We call f of t. Okay. Now there is a second picture that's slightly changing the graph, but you can see that it's actually the same f of t, but we change graph a little bit. And then the question is, what is this function? So if this is f of t, then what is this function? Okay. Now please think and look at these two differences. What is the difference? Okay. So let me just review what we already have in the unit step functions. Okay. So first, we can consider that the change are happen from interval 0 to a, right? From the interval 0 to a, this is getting 0, right? Getting 0 value. So the function is 0 when in interval 0 to a. Okay? This is what happened when your function is getting multiplied with the Heaviside. Okay? So we can say that this is f of t getting multiplied, or let me write multiplied with t minus a. Remember that according to our definitions, our unit step functions, it might have two two um, two different definitions. It's getting 0 or it's just as it is. It's equal 1. Okay. Okay. And now, if I take another approach, I take the 0, the effect. Aside from this, we have also after b. So we have 2 points that is getting 0. Now what's happened here? We can say for the first case up until b, it's the same with the previous one, with this one, with this. Okay, it's the same. So we can write f of t, Heaviside of t minus a. Okay. And then the next part, what we are going to do, remember that it's getting 0, so we can multiply and we can subtract. Actually, we can subtract with its function. Okay. Remember, now the idea behind of this is to see the interval. Okay, so this is zeroing the 0 uh, to a, and the right one is that. Okay. Now how to make this logically make sense is you can imagine any t that you can have. Okay, so this is from t is, so if you can imagine that this can be equal to 0 or 1, right? When this is 0, then it's just the left functions, right? When it is 1, then f of t minus f of t is 0, right? So it's getting 0 value at the bottom. Okay. So I hope you can get the idea on how to make. I think the first one is easy. It's nothing new. But if you have another functions that has zeroing part on the right side, then you need to subtract and then multiply with the t minus the t, the point that is going to be 0 from its point to the right side, to the infinity. Okay. Another variation that we might have is if we are having if this is f of t, we can also have, for example, we can also have f t minus a, which means we can shift the graph and make a new graph and then shift it maybe from here and make the same graph like that. It's shifted. And also we can also combine this with the happy side. We can also combine with the happy side. For example, we can also combine this with let's say we have the we combine this with the t minus a, which means that this is going to be 0 here. Or if you want to shift it with b, we can have, for example, from here, making the same, that is ft minus b. And if you want, we can also make 0 from 0 to b, and we can write this is happy side t minus b. Okay, let's run something. Okay, so we can shift the graph. We can adding the happy side. Adding a happy side means that we are adding this type of functions here. Okay, that's the meaning of the happy side. Okay, and if you have two happy sides like this, which means we are having construction of the function minus another function. Okay, and of course you need to also remember that if you're given a graph or given a piecewise defined functions of some cases, you can develop the function at its happy side, and you can write like this. And for whatever question it is, maybe it's asking what is the Laplace of it, and maybe you need to transform. You should be able to make that happen. Okay. Just a little bit review. Okay, if you have any questions. Okay, let me check. Okay. Okay. Another reminder on Laplace. If so, some of Laplace. Or maybe let me start with the happy side. Okay, let me start with the happy side. Where is happy side? Okay. Okay. Recall. Okay, just recall what we have is Laplace. If we have the happy side, since we have E minus AS over S. So if we have inverse, this is F of T minus A, and then happy side T minus A. The alternative form is Laplace G of T T minus A E minus AS, and then Laplace of G T plus A. This is also can be done. Or forgot the first one. Right here. Laplace ft minus a t minus a e f of x. Okay, the first one, and then we can inverse making this. Okay, so from this Laplace and happy side, if we have a question that is, let's start with this t minus 1 happy side t minus 1. We can directly go through the first steps. Okay, So we have E, right? E minus A is 1, so S, and then divide by S squared, right? Okay, so if we have another questions, if we have Laplace of t happy side t minus 2. Now, for this questions, we can have our Laplace becomes the first form here. We forcing the form to be the first one, or we can just use the second one here, the alternating form. So let me just write the first one if we want to use that. So t minus 2. So we make it the same t minus 2 and half a side t minus 2. And we need to plus to make sure that it's going to be the same. Okay. So we make sure that when we multiply this, this is getting the same structure as this. So we are getting this structure, right? So it's true that it's equal, right? It's equal. So we can add additional multiplications to make the first equation here. The first equation is the same, right? Okay. Okay, now we can move to this first Laplace, or we can write it's actually Laplace of this plus 2 Laplace of this 3 minus 2. Okay. So the first one we are having e negative 2s divided by s squared, right? Because it's just e, and then plus 2. This is e negative s, right, over s. And this is actually our answer. Now, if we want to make it into the alternative forms, we can just write. So let me write the question again here. Happy side t minus 2. Okay, let me move a little bit down. Okay, alternatively, we can write that this is equal to, we can directly just write this. Okay, so a is 2, so negative 2s. Okay, and then Laplace of, we can directly write the g t plus a. So it's become t plus a. So we can write a function. So the function is function g here. So our function is t, right? Just t. So we can just write t becomes t plus 2. So t plus 2. Okay, Laplace of t plus 2. So Laplace of t is just 1 over s squared, right? 1 over s squared. Laplace of 2 is just 2 over s, right? And I believe this is the same answer, right? Same answer as this. So you can choose either you forcing to be the same as the first forms, or you could just use the alternative forms. It should be the same result. Okay. Okay, I think one more example for this one, okay, for the Laplace, and then we can move to the Laplace Inverse. Okay, the next question is, we have Laplace of cosine 2t, and then Heaviside of t minus pi. Okay. Okay, probably we can have. I will give you some time. Okay, maybe 1-2 minutes. Check. The first thing you can do is maybe taking the cosine into a trigonometric, an alternative trigonometric forms, and then directly to write the answers. Okay. So it's also the same as before. Okay, you can directly write as the previous question as this one. So you can directly write e negative 2s negative as. A is pi, so negative pi s, right? And then Laplace. The function is cosine 2t, so we can replace t with t plus pi, so it's become cosine 2t plus pi. Okay. Okay, now if we have t plus pi, we can just say that this is actually just equal to Laplace, okay, Laplace of cosine 2t. And this will be equal to cosine 2t is s squared plus 4. Okay, now alternatively, besides directly goes to these forms, we can write this Laplace and make it, we force it to make it using some trigonometric alternative forms. We can make it, this is t minus pi, and then Heaviside t minus pi. Of course, from here we can directly write it's e. It's the same thing with this. Okay, e with negative pi s, and then cosine of 2t minus pi. This is the same as s over s squared plus 4. So meaning that this is the translations pi, and this s over s squared plus 4 is actually from Laplace of cos 2t. Okay. Okay. Okay, any questions from this one? Any questions? And I sent you your quiz result yesterday. Let me know if you haven't got your email. So usually after exam, I will send through email. I'm using the one that you gave me before, your preferable email. But if you don't give me I will send you to the NTUST email. Okay, you can check. Maybe you can check the spam folder, because I'm using just my personal Gmail. So maybe it sounds like a spam because I send using automated email to uh, all the students directly. So maybe it sounds suspicious by your system. So maybe it will be in the spam folder. Okay, now I think the way we learn Laplace is if you can make like special table for all Laplace, okay, like from the basic Laplace, the inverse, and then the translation involves the derivatives, right? If you remember the derivatives, and also the translation involves the Heaviside function, and also all the inverse, and then convolutions. The last part is convolution, and also its inverse. I will mention later after this review. If you can make that in your notes, like maybe you can have like maybe A4 paper, you can write some table of Laplace. It will help you, I think. I think it will help you. Okay, so you can rearrange uh, your forms, and in whatever question you have in Laplace, you can just look at the table and maybe you can rearrange based on the table. Okay, I think that will help. Yeah, that will help. Okay. That will help at least to rearrange the Laplace and Laplace inverse. Okay. Because if you are just taking from your memory, if you just remember a little bit, it will be difficult to rearrange the Laplace. If the Laplace like combined with different structure, it's also the the equation seem complicated. But actually, it will be not complicated if you have this table and then you can rearrange as much as you want. So that's my suggestion. So make a paper. I think A4 from your notes, just for Laplace, and make the uh, all the basic Laplace, the translation, uh, the convolution. Okay, okay, that's my suggestion. Okay, the next is if we have the inverse, what can we do? So we have, for example, Laplace inverse. Let's say we have e with power of negative 2s divide s cubed. Now first we remember that the Laplace inverse is this. Laplace inverse of e negative as f of s. This is the very basic inverse, right? The very basic inverse. This is equal to f t minus a Heaviside t minus a, right? Okay, now looking at this s cube, probably the inverse of this is having, remember that when you have something that has, for example, 1 over s, probably that will be just a constant, right? But if you have something that has maybe squared, cube, maybe this will be equal to t squared, right? If you remember the basic Laplace. So from those relations, then we might have, maybe we have another t with power of something for power of constant, right? And here, the t is translated 2, right? Translated 2. The a is 2. So it's actually, this is a is 2, right? So maybe we can write down that maybe we have since it's the a is 2, so maybe we have t minus 2 something, right? But before we write the t minus 2, we can write clearly to see the change of this s cube, because if you have s cube, we need to have the at least 2 factorial, right, to make it happen, right? This is the t squared. So we make multiply with half, and then 2 to make it clear, and then 2 with over s cubed, and then e negative 2s. This is to make it clear. So half will be in the just a constant. Oh, sorry. Make it a little bit right. The Laplace inverse. So half, okay. And then the 2 over s cubed, this will be our t squared, right? So because it's translated with a equal to, so the a is here, not this 2, and the a is here, negative, this 2s. So we need to translate t minus 2 squared, and then happy side, t minus 2. Okay. Okay. Then we have a little bit more complex. 1 plus e negative 2s, and then squared. Oh, let me make the bigger. Then s plus 2. Okay, what will happen here? This basically because of this square, we need to expand first and see what kind of fractions we have in each if we separate things. So this is 1 plus 2 e negative 2s plus e with negative 4s. Okay. So we will have 1. So let me write Laplace inverse. 1 over s plus 2 plus 2 e negative 2s, s plus 2, plus e negative 4s, s plus 2. Okay. 1 over s plus 2 is easy, right? We know that this is from e power of lambda, right? Lambda theta, or we can write this is from s minus 2, right? So we write e with power of negative 2t. And the middle one, we can write this is according to the structure. According to the structure, we have the a is 2, right? The a is 2. So we will have the translation t minus 2 in here, right? And the s plus 2 here is from s minus 2. I hope you understand the little notes here, that the clue that I gave you, that you need to at least get the idea. Okay. So this we can write. This is plus twice of. We have the functions is the same e, right? The function is e with power of negative 2, but the t is translated t minus 2 because of this a equal 2, and then we need to also write its translations. Okay, its translations like that. Okay. Now the last one is the same but different a, so we can write plus e negative 2. Now t minus 4, and then the happy side is t minus 4. Okay, and that's our results of the inverse. Okay. Okay, I think for the inverse I will stop here. And the next thing is I think I haven't give you the convolution, conclusion, and example. Okay. Okay. Okay, recall the convolution theorem. That is, let me just write the formula. This means f convoluted with g. This is equal Laplace f of t and Laplace g of t. So what makes convolutions special is when we Laplace those convolutions, we can separate the convoluted variables or convoluted functions with its own Laplace. Or we can say that this is equal okay, and the convolution itself is basically the meaning or the definition. If you have f convoluted g is integrations from 0 to t f, this is tau. It can be any variable, but it's like a dummy variable if you remember the fundamental of calculus, theory of calculus, right? And this is t minus tau. Sorry, functions. Function g and then the tau. Okay, now from here, what I want you to look at is maybe just a notion what will happen. Okay, so when we have, for example, we have a plus et convoluted with sine t. This is, we can write Laplace of each et and Laplace of sine t. We can have e with power of t is 1 over s minus 1. Sine t is, let me just write with this, s squared plus 1, right? And we can just write s minus 1, s squared plus 1, and then that's the result. Okay, now if we can Laplace, we can make the theorem for the inverse version of this, right? Now the inverse of convolutions, let me just start with the fs capital, and this will be equal to the convolutions. Okay. Okay, let me give you some sort of example. So if we have Laplace inverse of 1 over s squared plus k squared and then squared. K is just a constant, and so k is constant. So the first thing we can do is we need to identify what is going on inside, right? So let me just write what's happening here. So if we can take this as capital F or capital G because it's the same function. So if we take this and make the function is equal to s squared plus k squared, and remember that if we have this kind of function which k is just a constant, we can make it into our sign, right? If you Laplace this, okay, if you Laplace this, we have sign. Okay. Now, when we have we want to Laplace this, let me write with Laplace of or Laplace inverse of this. This is we call the f, let's say ft, like that. We can have 1 over k, and then I think we can just directly write, or let me write 1 by 1 is k n squared plus k squared, right? To make the calculations equal. So it's become sine kt. So this is f of t and also g of t, because they are both the same, is equal with this. Okay. Now from this, we can make into our Laplace inverse. So probably I will write here. So Laplace inverse of 1 over s squared plus k squared is equal. Now 1 over k, I will, because we need to multiply both, right, like this, right? So we will have 1 over k squared, and based on what we have, okay, in the convolutions, remember that convolutions we have uh, this meaning. We need then to give you this is f, okay, f, let's say k tau with the dummy, and sine k t minus tau d tau. Okay. Okay. Now for sine, and for other questions that has trigonometric multiplication, we can have trigonometric special forms, right? So we can have for sine, we remember that sine A, sine B, we will have half cosine A minus B minus cosine A plus B. Now doing the same thing, we can make this setting the A. So A is k tau and B is k t minus tau. So we can carry the Laplace inverse one over its half goes outside, is 2k squared. Now the inside becomes cosine A minus B, so k tau minus kt. Let me maybe make it simple to see. Okay. So a minus b is having two tau, right? So cos k, this is two tau minus t, and minus cosine. If we plus, it's just kt, right? Just kt. If we plus, it's cancelled in minus. So this is the whole thing, the tau. Okay. Maybe taking this a little bit down, maybe there. Okay, now we can continue. This cosine and minus cosine, what will happen here? I think we can integrate first. Okay, we can integrate. Now what we need to integrate is we need to integrate with respect to tau. So tau is our variable. So careful, this is not our variable. Okay, so our variable is only tau. So the results is cosine k. This is 2 tau. So it's actually like this. Remember, maybe just write like this. Okay. So it's becoming sine, right? Positive sine k 2 tau minus t, and then divide with 2, right? Divide with 2 from the inside variables. So 2k. Okay. Because k is still in the variables. This is actually 2 tau, or if you want to write, maybe better write with 2 tau k minus kt. Okay. And then minus, this is just not having any tau, right? So we need to add cos kt from 0 to t. Now adding all this thing here, so when we add t, when we put t inside, it's becoming sine kt, right? Sine kt over 2k minus tau, not tau, t, sorry, t cos kt. And then adding 0 inside, minus sine k minus t 2k minus 0. It's become minus positive, right? Positive, positive. So it's become sine kt over 2k plus sine kt over 2k, right? So it will be canceling this. So we will just having sine kt over k minus t cos kt. Okay, that's supposed to be this. So we can have sine kt. Let me just divide with 2k cubed, and then this will be having another k inside to make it happen. So this just to multiply with k cos kt. So this will be the Laplace inverse 1 over s squared plus k squared squared. This will be the Laplace inverse. Or if we multiply both with 2k cubed, another form that we might have sine kt minus kt plus kt, right? So from here we can also say Laplace of sine kt minus kt cos kt is equal to 2k cubed divided by s squared plus k squared squared, and this become one of very important Laplace. Okay, one more on the convolutions is about the integral, the transformation of the integral. Okay. Okay, so next is the transform of integral. So Laplace, let me write maybe. So when g of t equal 1 plus gt equal gs equal 1 over s. Right? And then the convolution that implies with Laplace of integral of f, can say that we have Laplace integration. So if we take the g is equal 1, okay, if we take g equal 1, so this will be equal to f of s divided by s. Right? Because of Laplace of g is 1 over s and Laplace of small f is capital F. So we can multiply both, becomes capital F divided s. And that will be our transformations when we are having integration. And from here, we can take that the Laplace inverse of f of s divided by s is integrations of the f. Okay, so basically, this is just another form using the convolution property. Okay. Now, if we have Laplace inverse example, Laplace inverse 1 over s and then s squared plus 1, we can think this from Laplace inverse. So basically what we are going to do is we check whether we can make this f of s over s. So we can take this. Imagine that this is actually from here. Okay. So we know that 1 over s squared plus 1 is just sine, right? So we can have our integration of our functions that is sine. Let's say we have tau d tau. And then this will be becoming cosine, right? Becoming cosine. Negative cosine tau from 0 to t. So this will be equal to 1 minus cosine t. So whenever you can make the inside of a Laplace inverse becomes a function divided by s, then you can write the integral of this f, small f, okay, f of tau. Another example. We can make it into our, let's just say if we have this s at the bottom, so the rest will be having 1 over s squared and then s squared plus 1, right? So we need to know this. So probably let me just write another one here. Before that, should be having the 1 over s squared plus 1. One over s squared plus 1 and divide by s. Now remember that this is precisely the same thing as this, right? The top one here. Okay. Now we can write this function is actually this, right? So we can write here 0t 1 minus cos tau d tau, right? And then we can write this is become t minus sine t. And the same thing with what the second question has. This s squared plus 1 is actually from here, right? So we can write integrations of tau, or maybe from here, actually here, sorry. So tau minus sine tau d tau. And we have half t squared minus 1 plus cos t. Or if you want to make it 1 by 1, okay. So this is one example. There is another formulation, however. It's called the Volterra integral equation, but I will skip that. I think I just stop until here for Laplace integration. The next part, also skipping the periodic functions. I will skip that and go for the Dirac Delta. But I think Dirac Delta is just giving you a brief introduction. So I think our exam will not be also included the Dirac Delta, but I will just give you information. Okay, so this is the transform of integral. Okay. Okay. The Dirac Delta functions. I think we still have time. So the idea behind the Dirac Delta is actually it came from uh, before we have um, the step functions, right? The step functions. The step functions, if you remember, it goes from, let's say, it's going 0 until some part, and then it's going to be 1, right? We say that this is our step function, and maybe this is a, then we can say a heavy side t minus a, right? So it can be 0 or 1. This will be 60, and this will be t greater equal 1. This is our heavy side. So if you notice, okay, if we can imagine uh, at a, okay, at a, at a, there is actually some rate of change happen instantaneously from 0 to 1. So can you imagine that? So imagine actually if you are looking at this point A, it has some explosion, right? From 0 and then suddenly it's 1. Okay, from 0 to 1. So at A, let me write with quotes just to give you some idea that explosion happened, right? Or the magnitude the magnitude happen in very short time because it's only happened at just one point, right? We call that in mechanical system, it's like an impulse. It's like an impulse. We call this an impulse. But of course, if you want to get the idea of what this impulse is, we need to define into a new visual graph. And we are not using the happy side. We need to give another terms or another name to make this impulse defined, to make it more defined. So what will happen here is, let's say we have at some point here, this will give you, let me just give you this line here. So it's simply say that uh, at this short point, as you say at A, it gives you an infinitely large magnitude. Okay. Let me just write this in terms of t0, okay, to make it clear. And then we call this as a delta, And since this is at this t0, we are going to remember that we translated like in the happy side. So we have t minus t0. And let's say this is a delta A. Now, if you notice, we have 0 from this interval, right? And 0 also from this interval, and we have something here at this t0. And if we can make some small part, so if we take this line, this green line, we take this and then cut by pieces, like we have it done in integral. So let's just make it like a rectangle. So let's say it's very small, but we can imagine this as a rectangle like that. So we have some sort of, let me just write it like this. We have for example, we have this rectangle here, okay, and we say that we have a certain if this is t0, this is a, this is minus a, okay, which means that this is t0 plus a, t0 minus a. Okay. Now let's say that this is equal to 1 over 2a. 1 over 2a. So this definitions. Okay, let me just write first. Let's say 0 from 0 to t, and then to t0 minus a. So in here is actually, maybe I will also make another notion that we can have this let's make this as a rectangle here, that we have this is t0 minus a, t0 plus a. So it can move a to the right, a to the left. Okay, now this is happen here. Now the delta, let's say the delta, we say that it's equal to 1 over 2a from t0 minus a until t0 plus a, and then after that it's going to be 0 again. Okay. Okay. This 1 over 2a, what now the question is why this is 1 over 2a. Now that is this question, interesting question, right? This 1 over 2a is actually the property of the if we can, maybe let me just give you this short summary from the heavy side, okay, to give you an idea why this is, we can connect these two. Okay. So actually from this heavy side, if you want to connect with the delta, our delta function, let's say delta t, is actually our derivative of the heavy side. Okay. So what we are remembering, okay, if we look on the delta, that if we integrate from all point, okay, if we integrate this, it's equal to just this point, right? Just this point. So if we want to integrate, since we can integrate, so integrate, so this integration will be just the heavy side, right? The heavy side. So the heavy side from, or maybe let me write it t, the heavy side from t negative infinity to t equal infinity. But remember, the heavy side, we only, if we integrate this is just saying that when t is infinity and when t is negative infinity, it's just 1 and 0, right? This is just 1 minus 0. As we can see from here, is 1 and 0. So the idea here is the integration itself is just 1. Okay, just 1. Okay. Now you can get the idea now, because it's 1, so we need to make up something. Okay, we can make up something that when we integrate here, when we integrate the all interval, so let's say we have the delta t. Let's say we make the delta t, which means that this is precisely on the 0, like this. Okay, just to give you an idea, and we can connect to our formulation here. So this is actually saying that this is integration from, let's say this was negative tau and tau. Okay, because in all interval, the only way we can integrate is just looking at this two interval, right? So we can integrate and adding here negative tau, and then there is something here to define our delta, so that the equals should be 1. Okay, so that it should be equal to 1. So if it is just a constant, here to give you an idea, so we need to multiply with something that when we doing the integration with respect to t, we are getting the results 1. So the something inside is we can take as just a constant of negative 1 over 2 tau, because if we are having, let me just write x. Let me just write x to give you why we get this 1 over 2 tau. Let me just give x. Okay, x is just a constant, so we can just x and then t from negative tau to tau should be equal 1. This will be equal to tau minus tau. It's 2 tau. So 2 tau t, or 2 tau x, sorry, is equal 1. So x is 1 over 2 tau. So this is why we need 1 over 2, 1 over 2a. Okay. So that's why we have this 1 over 2a here. Okay, I hope you get the idea of where it's come from. So this becomes a new piecewise definitions for t minus t0. Okay, so now minus t0 means we just translate from the middle, the 0 to t0. Okay, So we call this is unit impulse. And again, that the unit impulse, let me write here, it has the property equal 1. Okay. And as illustrated, maybe I will just illustrate in the new page. Okay. Okay, so maybe let me just rephrase this in the new way that we have. Okay, now this is actually how we can get the 1 over 2a. Okay. Because the integrations supposed to be equal to 1. So we need to define the rectangle like this one. What is going on here is when we take a as a is getting 0, a is this unit here in between of t0 to the rectangle side. So as a is getting 0, as a is getting 0 means that a is getting smaller and smaller and smaller, right? So when a is getting smaller, notice that it has height of 1 over 2a. So when a is getting smaller, the height is getting higher. Okay? So when a is getting smaller, right? Getting smaller here, it's getting higher, right? It's getting higher. When a is getting again smaller, it's getting higher, and it's getting higher and higher and higher. So imagine the explosion that can happen at instantaneously at point this t0. Okay. So at t0, you see that it's, let me write this, infinitely high. But I will write it with quotation because it's kind of ambiguous, because we make it seems not really infinite, but when we make it smaller, we get infinitely high. So the Dirac delta from this illustration, we can write the Dirac delta function. So as the delta t minus t0 is equal to limit as a is getting 0, the delta a t minus t0. So we limit the size of the interval of the rectangle. So when we take it into 0, getting 0 and 0 and closer to 0, the height is getting infinitely large, which is actually the same idea when we define the what happened in the Heaviside functions, right? What happened in the Heaviside functions, at one moment it happened, the change from 0 to 1 instantaneously. So if we try to manipulate with derivatives, what happened is we are having the integration of the Dirac delta is supposed to be equal to 1, okay, as in the Heaviside function. So in our imagination, it seems that it's going really, really fast and instantaneously fast. Okay? And when we imagine this visuals with the rectangle, to make it going infinitely high, we need to make it the sides getting small, okay? And then as a consequence, the height is getting higher, okay? Because we need to compensate all of this multiplication need to be equal to 1, okay? Now we can write the expressions. We can have the some property that is from previous cases. We have this can be equal to infinity and 0. So when it's equal to 0, as I said before, it's infinitely high, right? It's infinitely high. But when we take it another t, it's just 0. So the impulse happen when it's going to be equal at that point. At that point. And another point is the integrations. The integrations of from, let's say, from 0 to infinity of our Dirac delta is equal 1. Okay. Now there is one transformation with Laplace with Dirac delta. This is just one transformation. So delta t minus t0. This is e negative s t0. So it seems similar to what we have before. The difference is before we have the Heaviside, right? The Heaviside. Since we know the delta is the derivative of the Heaviside, we can take the this Dirac delta and then change into the Heaviside. So we can take, let me make this. Okay. So the Laplace is just this. The transformation is just this. We can take the Dirac delta as 1 over 2a and then write up the inside. Now, if you take Laplace of this, Laplace of this becomes e. It has transformation with a. Okay. With sorry, not a, t0 minus a. So s t0 minus a divided by s minus e negative s. This is t0 plus a. Divided by s. And then it becomes e negative s t0. This is 2sa, and then this is e negative a or a positive a, and then negative e negative sa sa. Okay, now we have this as our Laplace, and we know if we see this using the limit, if we see that this is getting in determinate form, if we apply a getting 0, then we will have 0 over 0, right? 0 over 0 situations. So because it is 1 minus 1 is 0, and the bottom one is also 0. So the one way we can do is we take the L'Hopital rule. So take L'Hopital rule. So take L'Hopital, and we can write the Laplace of the delta limit a going to be 0. Let me write the constant is e negative st0 is a constant. So limit, and then this will be 2 sa e sa negative e negative sa. And then this is equal to, so we take the L'Hopital rule. So we are going to derive both of these two, and we will be equal to 1 later on. So this will be equal to negative st0. So from here we can conclude that this is going to be our transformation. And also from here we can take that if the if t0 is equal 1, what will happen? If t0 equal 1, it seems that, or if t0 is 0, if t0 is 0, so we can take the Laplace of the delta t is just 1. And I think this is true from our conclusions here. This is equal 1, right? Okay. Because your textbook, I think it didn't directly, it's not directly mentioned that the delta is the derivative of the Heaviside function. So I think I need to mention this to make it clear, okay? Because your textbook didn't mention it at all. Okay. So I think the Dirac delta, although I said before it's not included in the exam, it will include, but really just like really small, really small. So finish the Dirac delta, and the next section is supposed to have the system of linear differential equation. I will skip that. So Laplace will be focused on Laplace itself, uh, how to inverse, the translation theorem, convolution, the Heaviside functions. Okay, and that's all for Laplace. Okay. Maybe any questions? Any questions? Okay. Any questions before we move to new materials? Okay, so the new materials, um, it's supposed to be factors, but I think I will skip factors. Heaviside will include the Dirac delta. The Dirac delta will include, but in small portion. The Dirac delta. Okay, so I will just review all the matrix, okay, the matrix, okay, and then we can focus on the eigenvalue eigenvector matrix. That's the idea. So I hope, okay, I hope you are able, or you have studied before from the matrix algebra, okay, the determinants, inverse, Cramer's rule. Cramer's rule we already used before, right? In um, in the higher order differential equations. In one way, we use the Cramer's rule to solve, right? I think in the variation of parameters, right? We use the Cramer's rule, uh, and then eigenvalue, um, orthogonal matrix, and diagonalization. That's all for matrix. And I hope we can finish just by I hope by today we have just some sort of brief introductions, and next Monday we can have more, and then move to the factor calculus. The factor calculus. So matrix is just a few sections, okay, because I believe the intro of matrix not really needed because I believe you're familiar with matrix. Okay. Okay. So the this session up until around maybe around 12, we are having just a brief intro to matrix, determinants, inverse, and then the afternoon session we continue a little bit of matrix, and then we most of our class next afternoon will be reviewing the I think higher order differential equations, okay, to give you more exercise and practice. So what is matrix? Okay, what is matrix? So matrix is, we can write a system of linear equation or maybe of vectors in an array, uh, in a horizontal or vertical array with so we can write like this, or a vertical array. Okay, so this is the matrices. Or in a more general, the general forms we can have, let's say we take A11, okay, to name the matrix. It means that row 1 column 1, okay, row 1 column 1, and then 1 2, it means row 1 column 2, and then it's supposed to be row 3 and so forth, and we take this as 1n, okay, and let's say this is 2 1, and then until some n column 1. This is the same thing until the n, or maybe not the n, maybe m, okay, to make difference with the other one. And then this is column 2, and then the rest here is mn. So this is matrix by, or maybe matrix m by n, right? So the row and column. So I hope this is familiar and you already know how. Okay. But if you remember, matrix is like we use the same terms matrix in cells, right? If you remember, we have extracellular matrix in biology. So matrix is kind of space, actually, like a space, uh, like an environment. We can also say that. So this is actually it's it's environment, but in our case in mathematics, we make the environment made of a numbers that is written by row and column. So it's like environment space. In the and actually matrix came from the word like from mother. Okay, it's just a brief intro. Okay, so like a mother. Why mother? Mother has a womb. Womb has an environment for the baby. So it's like you have a baby here. Okay, but it's supposed to be uh any any definition that can have something in spaces. It's and we define those space in a way with numbers. And numbers is just an abstract, right? Abstract thing that we can define with. If we define with 1010, it's become our binary system in computer, right? In chip, right? So that's just one way to look at this matrix. So matrix is not just always, if you imagine like, okay, we have some sort of numbers and we can compute, we can calculate. It's not just of that. Okay? We can apply this matrix into any other forms actually. Okay, the numbers is just our definition. Okay? When we define, maybe we define matrix in color. So when you have a color, we define with some numbers that maybe with that numbers, the contrast or the brightness of the colors will be also shown. Okay, maybe it will be getting darker, getting lighter. Like when you deal with the some software, okay, like using some maybe you familiar with Photoshop, Illustrator. When you transforming your design, it's actually using something that need to be defined, right? And the easiest way to define that is making the environment into a number, and that is the matrix. Okay, I hope that can give you more idea. Okay, so we are not just calculating the numbers, but we are actually trying to see what is happening in our real world. Okay. 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 One thing to remember in matrix is if you want to multiply the matrix. Okay, if you want to multiply the matrix, let's say we have matrix A and B. Okay, we need to multiply the row and column. So let's say uh, let's say A11. Let's say this is having another one. Okay, and this will be matrix B, B11, B. Uh, this is 1, 2. Sorry, this is 1, 2. Oh, it's not A. Sorry, B. Okay, the way we multiply matrix, we multiply with this row, multiply with column. So the row and column numbers to make this multiplication happen need to be equal. Okay, need to be equal. Okay, need to be equal. So this way we can multiply. This means that A11 B11 plus A12 B21 and so forth, okay, and so forth, and then plus dot 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 until the end, and then the rest is the next row. the next column. Okay, and the next row, the next column. Okay, and then you will have at least 3. Now you have the matrix will become 3 if we have this 1, 2, 3. Okay, so this is the second one, and then the third one. Okay. If we have 3, okay, but if we have more, then we will have if 4 row, then we will have 4. It depends on how the numbers in the matrix. So we can write that A with some row M multiply with B matrix with some row of N. This will be C M N. And let's say A is M by P column and B is P row by N column. And you can see that we can ignore the P, so we can just focus A for its row, B for its column, and we can make it into M by N for the new matrix C. And we can make this matrix to set up our system of linear equation. For example, if you want to set up system of linear equation xy, we can set up by negative 4x plus 2y, 3x plus 8y. So we can have our system of linear equation also. And we may have associative law, and we have distributive law. I think it's best if you maybe taking any matrix and then try to define. Another important in matrix, aside from the basic algebra, is the transpose. Because transpose means you are going to rotate or changing the row and column. You exchange the row and column. Okay. So usually you have, let's say, A is A11 is supposed to be A12, A13 until A1n. This is AMN, right? The A transpose supposed to be written like that, with P in superscription. We can write it A transpose. What we're going to do is we make this row, the first row, the first column becomes the first row, So A11, A21, okay, A31 until AM1, okay, and then we are writing all. So we have A12, A22 until AM2. So we are going to see that this is getting A1n, A2n until AMN. So notice that the first and the last, the left top and the bottom right, is still the same. Okay, but the other part is going to rotate and exchange. Okay. So example, if A is 9,043,7,5, the A transpose is, remember we take the 9, 3 into row, 0, 7, 4, 5. That's the transpose. Okay. Another, if you transpose twice, transpose, it's going back to the original, right? If we take A plus B and then transpose, we can transpose each part and then plus. If we transform as a multiplication, we can have we can make it into B transpose A transpose, and we have a scalar transpose. K is just a constant, then we can make it a scalar outside and then A transpose. Okay, that's the transpose. And another special matrix that we have is this matrix 0. It's a 0 matrix. So example, we take this 0 with the bold characters and we can write like that. We can write also with different row and column, and it consists of just a 0. Okay. Matrix A plus matrix 0 is just A. Matrix A plus minus matrix A is matrix 0. So this is special matrix. And with we can have also, we call it triangular matrix. Triangular matrix. Okay, what's this triangular matrix? Let me just write a random matrix. Okay, random matrix. 1, 3, 4, 2, -1, 5, 1, 2, 3, 4. Okay, and let me write the rest of it with 0. Okay, this is we call, because we only have the half part, upper half part, we call this as upper triangular matrix. So you will notice that if you have the lower part, then you will have lower triangular matrix, and the upper part 0. Okay. So we can call triangular matrix if there will be a zeros, okay, above half part or below the bottom one. So we call the triangular matrix. And when we have, let's say we have, let's say a 5 to 1 over 2, and the rest of this will be 0. We call this diagonal matrix. So diagonal matrix if the entries not on the main diagonal will be 0. So only the diagonal one has the number. We call it the diagonal matrix. And if we have, for example, 5, 5, and then the other one is 0, we can make this into 1, 0, 0, 1, right? This 1, 1 here is identity matrix. And the whole thing here we can call the scalar matrix. So identity matrix is for whatever matrix you have, if you multiply with identity, it will be just that matrix. Okay. And then we can also have symmetric property for some matrix. So if you have A equal 1, 5, 4, and this is equal to 2, 7, 7, 3, 3. Let's say that's our matrix. We see that the number match, and we can mirror through our diagonal, right? We can mirror through our diagonal. We can say that this is, if we take transpose, this become 1, 2, 7, 2, 5, 3, and 7, 3, 4. It's the same. The transpose is the same. We call this property is the matrix is symmetric. So matrix A is symmetric because A is the same as its transpose. So that's just introductions. Okay. Okay, the next part is the system of linear equations, especially using matrix. Okay. Using matrix, we call this the formulation is the row echelon form or augmented matrix. Okay. Augmented matrix. Okay. So this is just giving you some algebraic terms in matrix and some special matrix. Okay, I hope you'll remember this. The next part is we can call this is augmented matrix. Now augmented matrix, it's supposed to help you solving a system of equations, especially in linear equations. Okay, so for example, okay, let me just give you an example: 2x plus 6y plus z equals 7, x plus 2y minus z equal -1, and we need one more to make it solution. So because we have three variables, right? X plus 5x plus 7y minus 4z is 9. So we can rewrite this with matrix. So we can write, usually if we use multiplications, we are having, this is the constant, right? So maybe 2, 6, 1, 1, 2, maybe let me just write 4. It's -1, 5, 7, -4. It's supposed to have like x, y, z, and the right part will be 7, -1, 9, right? But we can just take out the x, y, z, And we can just write 2, 1, 5, 6, 2, 7, 1, negative 1, negative 4, and then with straight line, and then the right side is 7, negative 1, 9. This form is called the augmented matrix. Or we can say matrix of the system. And to solve this, we may use some operators we call the row echelon operator or the row echelon form. Or we can call elementary row operations. If you remember, it's related to the Gaussian elimination method or Gauss-Jordan elimination method. Basically, the same thing. What you're going to do is we need to make it into echelon forms. Echelon forms is, let me write. Basically, what you are going to do is you need to make this diagonal to be 1, 1, 1, and this lower part becomes 0. So you will see the upper triangular matrix. So this, I will say, this wants all to be 0, and this wants all to be 1. So that's the idea. Any method like Gaussian, Gauss-Jordan, they are all the same thing, just little differences between those, but basically the same. So I was just giving you the idea that this is need to be 1, 1, 1, or the other part is 0, 0, 0. Okay. So how we are making this make sense? Okay. Now to take this, let me use the new page, okay, to make sure that we can compute in one page. So let me write maybe smaller. So 2, 6, 1, 1, 2, negative 1, 5, 7, negative 4, and then the right part is 7, negative 1, 9. Okay. So what we are going to do in the echelon operators, or we are having the augmented matrix, and then using some eliminations at the end. Okay. So here we call this row 1, row 2, row 3. Okay. Now the idea is we can set our any row, we can plus or minus with any row. Okay, that's the idea. We can multiply by scalar and then minus or plus the other row. That's also we can do. And we can have some sort of combinations. But you need to be very, very cautious, okay? Very careful step by step, because making small mistake at the beginning will be maybe compensate with mistake in the very end. So we will have wrong conclusion. Okay? So let's say we are going to plus the row. So let's say we take the let's say row 1 plus row 2. Okay, let's say this is row 1 plus row 2. Oh, not row 1 plus row 2. Let me just give you my idea, okay? Okay, so what we want in this diagonal is we need to have 1, 1, 1, right? Now we have 1 here. So maybe we can exchange this is also what you can do. Aside from plus, minus, you can exchange row. So you can exchange row 2 goes up, row 1 goes down. So we can write the first one is 1, 2, -1, and then -1, and then 2, 6, 1, 7, 5, 7, -4, 9. So we exchange row 1 and row 2. So we are having 1 here. So it's good. Now the rest is, what we want is the 6 and -4 are also 1, and also this part is 0. So maybe we can concentrate on making these three numbers 2, 5, 7 become 0. What we can do is, notice that 1 and 2 we can subtract if we multiply the first row with 2. So 2 minus 2 becomes 0. So let's do that. So we can, let me write here. We can take -2r1 plus r2, or we can take r2 minus 2r1, same, and we can write I will just write this first row the same thing. Okay. Now the second row, I will use this operators. Okay. So 2 minus 2 is 0. And then 6 minus 4 is 2. And then 1 minus 1. So 1 plus 2 is 3. And 7 minus 2 is 9, right? Okay. And then this part is having 5, right? 5. And we have 1 here. So I will just multiply 1 with 5 so we can subtract. Okay. So we can subtract. So the next part is -5r1 plus r2. Or r2 minus 5r1 for this third row. So 5 minus 5 is 0. 7 minus 10 is -3. -4 minus 5, so plus 5, it's 1. 9 minus 5 is plus 5, become 14. Okay. Okay, now still we have this part, right? This part. This -3, what we can do now is, or maybe before this -3, we see first this 2. We can make it 1, so we can divide with 2. Okay, so the whole row we divide with 2. So all the operators, so you can operate each row, okay, each row. So whenever you add, you subtract, or whenever you multiply with some constant or scalar, you need to multiply all row, okay, with those rows. So when you operate in row 2, so all row 2 will be multiplied with the constant or divided with constant, okay. Okay. So from here, let me write here. I will divide this row 2, divide by 2. So we'll write 1, 2, -1. And then 0, 1, 3 over 2, and then 9 over 2. And then 0, -3, 1, 14. Okay. Now we can make this -3 0 by plus with 1 with multiplied by 3. Okay, so we can take this. So we can say that 3R2 plus R3. Okay. We write the same thing here. Also the same here. And we are going to change the last row. So 0 is 0. Negative 3 plus 3 is 0. 1 plus 9 over 2 is 11 over 2. And 14 plus, this one is 14 plus 27 over 2. So it's from 28 over 2, it's 55 over 2. Okay, it's a really good number. But notice that this part, we need to be 1, right? We need to be 1. So we are going to multiply with 2 over 11. So 2 over 11 are 3. So we are going to have 1, 2, negative 1. 0, 0, 1. And then 2 over 11, this is just 5. Okay. Now we see that from here that our solutions is, this is, if this is z, then z is equal 5. And then y plus 3 over 2 z is equal 9 over 2. So you can get y plus 15 over 2 is equal 9 over 2. So y is 9 minus 15 is 6. Negative 6 over 2 or negative 3. So the last part is x plus 2y minus z is negative 1. So x minus 6y minus 5 is negative 1. Sorry. It's supposed to negative 6. So negative 11. So x is 10. So we can get directly at the end using just a substitution. Or we can make another 3 numbers here, make it 0. So we will get directly for x, y, z, each solution. Okay, this one up until here is called just Gaussian. If we make this, making the upper and lower part 0, it's called the Gauss-Jordan. But because both method is actually using the same concept of operators, the echelon operator, so I don't mind if you are using in any method. Okay, so if you want to make it 0, we can also make that. So we can using some sort of expression. So to make it 0, then we need to plus this 2, right? Plus this 2 with this 1, right? So we need to take, let's say, R1 minus 2R2. Okay. So 1 minus 0 is just 1. And then 2 minus 2 is 0. And then negative 1, negative 1, negative 2. So negative 4, right? Negative 4. And negative 1, negative 18 over 2 is 9. Negative 1, negative 9 is negative 10. So this is the same. And we need to have these 2 components, right? 2 components. Okay, if you see, then we need to, we can multiply the rest of it. And I believe you can do by your own, right? So try to make this 0, try to make this 0, and then you can get directly what you want at the end, right? At the end. Okay, I'll just stop here. But just to show you that this is what we call the row echelon form, or the row echelon operators. Okay. Now there are some cases that the solution might not happen as easily as it will be. For example, if you have one, let's say we have these two variables. If you try to solve this using row operations, we are just getting, let's say at one moment, you see that it goes to be 0, 0, and then a number there. So this 0, 0 means that it's 0 some variable x1 plus 0 variable x2, or you can call xy also. It's equal 16. This is no numbers that can satisfy these equations, right? It's 0, but it's equal 16. So it seems that it's inconsistent. So we call this inconsistent. We call this inconsistent in general. And we say that this part has no solution. And then remember that we have homogeneous, right, in differential equation. In this system also we have a homogeneous system. So we may have a homogeneous system So homogeneous system if we have, for example, 2x1 plus or might be minus 4x2 plus 3x3. You can use xyz if you want also, but let me just write x1, x2, x3. Okay, this is what we call the homogeneous system. The right side is all 0. Okay, now we can write 2, negative 4, 3, 1, 1, negative 2, and then the right side is 0, 0. Okay, what we can do now is we are going to have it's not exactly if we have 3 here, it will be perfect solution, right? But this is having just two systems. We only have 2 systems. So what we can do, we can take row operators and make it this part here becomes 1, 1. Okay, and this part, this 1 and negative 4, let's take it 0. So later we will have what we call is the trivial solution and non-trivial solution. The trivial solution is when the solution consists of all 0. So as a reminder, we have no solutions if we have 0, 0 and number. But what happens if all 0, 0, 0? That we call the trivial solution. Okay, now let's try to solve this. I think we can take this one going up, right? So we can just change the row. So 1, 1, negative 2, 0, and then 2, negative 4, 3, 0. I think I make it too big, so I will make it smaller. Okay. So I want to make this to 0. So we need to minus the R2 minus 2R1, right? So the first thing is just the same. So you can choose which part that you want to change. You can change the first part, but no use, right? Because we want to have 1 exactly there. So I will just change the second row. So 2 minus 2 is 0. Negative 4, negative 2 is negative 6. 3, negative 2, 2 is basically 3 plus 4 is 7, right? And it's just 0. And again, we see that we need to have the 6 here going to be 1. So we need to multiply with negative 1 over 6, R2. So 1, 1, negative 2, 0, 0, 1, negative 7 over 6, and then 0. And then we need to make this 1 over here is 0. So we are going just to minus the R1 minus R2. So 1 still 1, 1 over 0, 1 minus 0, 1 minus 0, 1 minus 1 is 0, negative 2, negative 7 over 6, so negative 12, negative 7 over 6, so negative 12 plus 7 is negative 5. And still the same. Okay. The solution of the system here, we see that the x1 minus 5 over 6x3 is 0. And x2 minus 7 over 6x3 is also 0. Now, what can we do to make this happen? We need to make, because we need to define some of the variable as just t, so it can be any number. So let's define the x3 becomes just t. So we have x1 is 5 over 6t, and x2 is 7 over 6t. And then we can solve with this kind of solutions for this system equation. Okay? So whenever t we have, we can solve by x1 is 5 over 6t and x2 is 7 over 6t. Okay? So for so we will obtain if t is 0, what will happen? X1 is 0, x2 is 0, of course x3 is 0 because x3 is equal to t. So when this happens, 0, 0, 0, remember, this is we call the trivial solution. And if t is not 0, we get the non-trivial solution. It's kind of similar with what we have in the differential equation we call some solutions we call the singular solutions, right? The singular solution that makes all gone by zero, right? We call this is non-trivial solutions, or we can say that this if x3 is t, x1 is 5 over 60, x2 is 7 over 60. This is called the non-trivial solution. So I hope from this example we can easily identify what is trivial solution and what is non-trivial solutions. Okay, because this might happen also. Okay, this might happen. This is the homogeneous system. Okay, this part here, although we can write into echelon form, in the previous page, I say that we can write this as some matrix, let's say matrix A, and then multiply with the matrix X. X is the variable, so we can say that we can write as this form also. Okay. Now I will write something about this property for this system. Okay, maybe let me just give you time to write. If you want to write this. Okay, now okay, the property, okay, let A matrix A multiply with matrix X equal to 0. It's our homogeneous system of linear equations. Okay, first is if x1 is a solution of Ax equals 0, then so if we multiply with this scalar or constant c for any constant c, and then the second property, if x1 and x2 are solutions of Ax equals 0, then so the x1 plus x2. Because if we simply look at this solution here, we know that Ax1 is 0, Ax2 becomes 0, so Ax1 plus x2, this is also 0, and becomes the solution. This is actually a matrix. Okay, matrix. And we can write down by taking these two property, we can also write down the superposition principle. Same thing with what we have in the differential equation. Superposition principle. So if x1 and x2 are solutions of Ax equals 0, then so the linear combination of c1 x1 plus c2 x2. c1 and c2 are constant. And if you have more like x1, x2, x3 solutions, then we have c1, x1, c2, x2, and c3, x3. Okay, maybe one more sections, and I think we have feedback. Okay, so superposition principle. But let me check first. I think I will just skip. There is one section in the matrix that called the rank matrix. I will skip that part because um, I don't think we are going to have more discussion about this. Let me just go for determinants first, and then if we see that we need to have the rank of matrix and we have time, then we can go back. So the next part is the determinant. So usually we can write the determinant as, so if we have a matrix A, and we have A1, 2, and the same, this is n, the same n by n, right? N, like that. So the same row and column, then we can have our, so A is n by n matrix. So we can write the determinant of A is using the straight line like this, and using the same constructions. So we can write the symbols like that in the determinant. So if A is 2 by 2 matrix. So let me just define the first part. Okay. So determinant of A is A11, A12, A21, A22. This is we call calculate A11, A22 minus A12, A21. Okay, just I think review, because you already we already learned about this before, and we already used this determinant in differential equation when we learned the Wronskian, right? The Wronskian. We have the determinant of the Wronskian. And what happens if we have 3 by 3 matrix? So the determinant of A we can write the determinant of this matrix. We can express this in terms of, let's say we are consider row 1. Okay, we consider this first row. So we are having A11, A12 and A13. Okay, so we can take A11. So the idea is to keep this row and column covered, and we are having this as our calculation, right? Our determinant calculation. So A11 is A22, A23, A32, A33. And then minus A12. So this is called the covectors. So we are having the covectors of this is positive, negative, positive, negative, positive, negative, positive, negative, positive. So it's actually positive here and then negative here, so it's become negative over there. So A12 and cover the row and column. So the row and column cover. So we'll have this A21, A31, and A33 and A33. So we have A21, A23, A31, A33. And then plus A13. This is A21, A22, A31, A32. Okay, and then we can solve this and make the equations become, this is A22, A33 minus A23, A32. And do the same thing for all of this. Okay. There is actually some sort of equation for the covector to determine plus minus, but just use this plus minus plus minus. I think the same. It's too many formula will be not really useful. Also, you can also configure with the third row, the second row or the third row. So maybe 3, 1, 3, 2, 3, 3. We can also make it. So it's actually the same, like A31. So we have determinant of A12, A13, A22, A23, and then minus A32, A11, A13, A21, and A23, and plus A33, A11, A12, A21, A22. We can also have the second row, but for the second row we are going to have negative A21 plus A22 and minus A23. Okay, the results supposed to be the same. Okay? Supposed to be the same. Yeah, it's the result will be the same. The result will be the same. If we have A21, then we are going to write negative A21. This will be A12, A13, A32, A33, and plus A22. This is A11, A13, A31, A33, and minus A23. This is A11, A12, A31, A32. Okay, that's the determinant. And I will just stop until here and we are continue later. in the afternoon class, a little bit of determinant, some property, and maybe some of the inverse of metric, and then we can have a review of what we have in Friday midterm. Okay. So I will just stop until here and hope everyone can have an enjoyable study. And since we are already in the matrix, actually my goal is to give you idea of eigenvalue and eigenvectors. If we not have much time for orthogonal and diagonalizations, that's okay. As long as I can give you the idea of eigenvalue and eigenvector. And after the matrix, we are having the vector calculus. We will start the vector calculus with curl, divergence, and line integral. That's the most important part. My goal is to deliver at least that sections. If you don't have time to have another more, then that will be our vector calculus, line integral, and then surface integral. For the Green theorem and the Stokes theorem, we will give you if we have time. But I think Green theorem we still have time. But for Stokes, I don't think we have enough sufficient time. So I believe we are just having curl divergence, line integral, surface integral, Green theorems, just until that. Okay, we will go to our feedback. Okay, so I hope you can prepare some paper. Let me go through here. Okay. Let me check. Okay, we have, I think, just 2 questions. Okay. So this comprehension will still be about the Laplace. And the afternoon session, the afternoon class, also the comprehension is a little bit about Laplace, because I want to know your feedback on Laplace, which part that we need to maybe be having more exercise if we have time. Okay, I think I can start now. Maybe let me check. Okay. Okay. Please use your student ID. Okay, student ID. So we have only 2 questions. Just 2 questions. So let's start by now. In 2 minutes, it's true or false. I gave you at the beginning of our class some of equations using cosine, right? But you need to check whether if it's true if this is sine. I still have 1 minute, 20 seconds. Okay, 40 seconds. Okay, 5, 4, 3, 2, 1. Okay, it's true. Okay, remember sine, you can change the cosine with complementary pi over 2, so it's just a cosine. It's become a cosine. Okay. Okay, remember to use your student ID, okay? For Thinky, Simba, Brand, The Broken, Nemo, okay, you need to change your student ID. Okay, next, the last question. Last question. Okay, 3, 2, 1, start. We need to have some sort of calculations now. Remember the inverse, okay, Laplace inverse of this e with power of negative 2s over s cubed. It can give you some sort of functions with some power and also happy side. So what kind of function is that? I think it's the same formula what when I give you in the first introduction in the morning time, right? At the early class, I give you, I think, similar to this formula, right? Careful on the signs, okay? When you plus the A, B, and C and D. So this is what will be typical questions, maybe in your next quiz. Okay, maybe I will prepare next quiz before the final exam. Okay. Yeah, the result is 0. Okay. 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 Who is Tinky? Who is Tinky? Okay. Who is Tinky? Okay, and then write your student ID, and then I would like to know whether the Laplace part too much or too overwhelmed. I want to know. So who is Tinky? Tinky? Anyone with Tinky name? Yeah. Okay, Laplace is getting harder. Yeah. Okay. Okay, if there is no questions, uh, I just want to know who is Tinky. Tinky. because I would like to include in the score system. Oh, okay, there it is. Okay, okay. Okay, I think we can stop here and we will see you later in the afternoon session. Okay, so thank you for joining for this class today. And if you haven't got your results, your quiz one, let me know. Okay, who is not yet getting. I already email, and you need to check email. Maybe going to the spam folder. Okay. Yeah, Tim, what's your problem? Oh yeah, the average. I forgot to mention. Okay, the average. Let me check. I think around 40. Wait, I already right here. Oh, the average is 46.4. Okay, that's the average. If you guys, you need to check. So if you below the average, below 30 or below 40, I think you need to be more, yeah, careful and do more study. And of course, the last quiz, maybe the time is too short and too much questions, so I will rearrange and give you with more adjustment. Okay. So if you get around 40 or 41, 42, I think still okay. But if not, then you need to be more careful, and please I remind you to submit all your homework, okay? All your homework. Okay. So that is for today. If there is no question, so I will stop until here and see you. Uh, oh,
Oh, Prof,
yes.
where can we get the link for the second homework?
The Moodle.
Oh, in the Moodle. Is
Yeah,
it
in the Moodle.
available? Right. Okay. Okay.
The Moodle. I
Okay.
put the Moodle. Usually the Moodle have the weeks, right? Week 1, week 2, week 3. I
Yeah.
put
Yeah.
in the second one. It's
Okay.
homework 2. Okay, you will see that. Okay.
Okay, Prof. Thank you.
Okay, material of the midterm is just the introductions, the differential equations, first order, and then the higher order. Just that. No Laplace. Laplace is for another quiz. Okay, another quiz. Okay. Okay, we will have review later. Okay, in the afternoon class for preparation for midterm. Okay. Okay, that is for today. So thank you.